Imagine floating in absolute nothingness, millions of light years away from Earth. Right in front of you sits a monster, a sphere of pure, unadulterated darkness, so massive that it doesn't just swallow light, it warps the very fabric of space and time around it. This is Gargantua. When Christopher Nolan released his sci-fi masterpiece Interstellar, audiences worldwide were left breathless by this visual marvel. For the first time in cinema history, a black hole wasn't just a lazy, dark whirlpool in space. It was a terrifyingly accurate mathematical beast. But it raises a mind-bending question. Could a monster like Gargantua actually exist in our real universe? Or is it all just Hollywood magic? Welcome back to Sleeping Galaxy, your portal to the deepest, most mysterious corners of the cosmos. Today, we are breaking down the mind-shattering physics behind Interstellar's iconic black hole. We will look at what the movie got 100% right, the terrifying detail they intentionally hid from you, and whether modern astrophysics has discovered a real Gargantua waiting for us out there in the dark. Before we cross the event horizon and dive into the math, make sure to hit that subscribe button and turn on notifications. Let's journey into the void. 1. To understand Gargantua, we have to look at how it was born. Christopher Nolan didn't want his VFX artists to just draw something that looked cool. He wanted the absolute truth. So, he recruited Dr. Kip Thorne, a legendary theoretical physicist who would later win a Nobel Prize. Nolan told Thorne, "I want a black hole that complies completely with Einstein's general theory of relativity." Thorne agreed, but under one condition. Nolan wasn't allowed to alter the physical laws of physics for Hollywood drama. What followed was an unprecedented collaboration. Kip Thorne wrote pages upon pages of mathematical equations describing how gravitational lensing works, how gravity bends light rays as they travel through a warped space-time fabric. He handed these equations over to Nolan's visual effects team at Double Negative. The calculations were so heavy and complex that individual frames took up to 100 hours to render. The visual effects software had to track thousands of individual light rays passing through a severely warped gravitational field. In total, the data for the black hole scenes alone swallowed over 800 terabytes. But when the rendering computers finally finished, something historic happened. The team didn't just create an iconic movie scene, they accidentally made a scientific discovery. When Kip Thorne saw the final render on a giant screen, he realized he was seeing phenomena he had only ever imagined in equations. The two simulation revealed a unique, asymmetric ring and light distortions that had never been modeled with such high fidelity. This Hollywood project actually resulted in two peer-reviewed scientific papers published in the Classical and Quantum Gravity Journal. Gargantua wasn't just sci-fi art, it was a legitimate, mathematically flawless simulation of a spinning black hole. So, what exactly are we looking at when we see Gargantua? Let's break down its anatomy. First, there is the pitch-black sphere in the center. This is the shadow of the event horizon. It represents the point of no return. Once anything, whether it's a stray particle of dust, an entire planet, or a beam of light, crosses this boundary, the escape velocity required to break free becomes greater than the speed of light. Because nothing can travel faster than light, nothing can ever escape. It is a literal trapdoor in reality. But if a black hole is perfectly dark, why is Gargantua so incredibly bright? That's because of the glowing halo surrounding it, known as the accretion disk. This disk is made of superheated gas, dust, and stellar debris that has been trapped by the black hole's gravity. Drawn into a cosmic whirlpool, this matter spins around the event horizon at a significant fraction of the speed of light. Friction and extreme gravitational forces crush this matter together, heating it up to millions of degrees, causing it to emit blinding amounts of thermal radiation and light. 3. Now, notice the shape of the light. It looks like a ring going over the top and underneath the black hole, crossed by a flat belt in the middle. In reality, the accretion disk is completely flat, just like the rings of Saturn. What you are seeing is an optical illusion caused by gravitational lensing. The extreme gravity of Gargantua is so intense that it bends the light coming from the back of the disk, curving it up and over the top and down underneath. You are essentially seeing the front, the top, the bottom, and the back of the disk all at the very same time. Gravity literally warps your perspective of reality. Think about how radical this is. If you flew a spaceship directly above Gargantua, the ring would morph and shift continuously, always wrapping around the black sphere to face you. It behaves like a dynamic lens, focusing and distorting light based purely on where you stand. This flawless representation of gravitational lensing is what cemented Interstellar as a milestone in scientific accuracy. But despite this incredible commitment to truth, Christopher Nolan hid a dark, terrifying secret from the final cut. As accurate as Gargantua looks in the movie, it is not what you would actually see if you stood in front of a real supermassive black hole. In Interstellar, Gargantua's accretion disk looks beautifully symmetrical. The left side glows with almost the exact same intensity as the right side. But according to Einstein's equations, this is physically impossible. In the real universe, Gargantua would look heavily lopsided, distorted, and visually terrifying. 4. This discrepancy comes down to an astrophysical phenomenon called Doppler beaming, or relativistic beaming. Remember, the matter in Gargantua's disk is spinning at nearly the speed of light. Because of this extreme velocity, the side of the disk that is spinning toward your eyes would compress the light waves it emits. This causes the light to shift to a higher frequency, becoming much brighter, more intense, and shifting to a harsh electric blue color. Conversely, the side of the disk spinning away from you would stretch the light waves out. This causes a severe redshift, making that side appear incredibly dim, dull red, and almost entirely invisible to the naked eye. A real Gargantua would look like a blinding, brilliant blue-white crescent arc on one side, fading into a ghostly, dark shadow on the other. So why did Nolan change it? Why did he leave out this crucial piece of Einsteinian physics? The answer is simple: audience psychology. When Nolan ran the fully accurate, lopsided simulation, he realized it looked incredibly bizarre and visually jarring. He feared that general audiences who weren't trained astrophysicists would think the special effects team messed up or that something was broken on screen. To preserve the cinematic beauty and avoid breaking the viewer's immersion, Nolan made a creative compromise. He instructed the VFX team to dial back the Doppler effect, smoothing out the brightness to give us the gorgeous, balanced cosmic crown we see today. It was a sacrifice of pure science for the sake of emotional storytelling. Now let's tackle the ultimate question. Could a black hole, exactly like Gargantua, actually exist out there in the dark wilderness of space? To answer that, we have to look at its specific metrics. According to Kip Thorne's calculations, designed for the script, Gargantua is a supermassive black hole with a mass equal to 100 million of our suns. Its event horizon spans roughly 300 million kilometers across, meaning if you placed it at the center of our solar system, it would swallow everything up to the orbit of the Earth. But the most critical factor of Gargantua is its spin. Gargantua is modeled as a Kerr black hole, a rotating titan spinning at an astonishing speed. Specifically, its spin parameter is set to 0.998. In the language of physics, this means it is spinning at 99.8% of the absolute maximum theoretical limit allowed by the laws of physics. It drags the very fabric of space around it like a swirling whirlpool, a phenomenon known as frame dragging. This near-impossible spin rate isn't just an arbitrary number. It was a mathematical necessity for the plot of the movie. Without this hyperspin, Miller's planet, the famous ocean world where 1 hour equals 7 years on Earth, could not survive. If a black hole with a mass of 100 million suns wasn't spinning, The gravitational tidal forces would tear Miller's planet to pieces before it could even establish an orbit. But because Gargantua spins at 99.8% the speed of light, space is stabilized around it, allowing a planet to orbit safely right on the precipice of doom. Do such extreme spinning titans exist? 6 astrophysicists believe the answer is a resounding yes. When we look at supermassive black holes at the centers of distant galaxies, we find monsters that make Gargantua look like a dwarf. For example, M87 star, the very first black hole ever directly photographed by humanity, has a mass of 6.5 billion suns. Furthermore, data collected from X-ray observatories suggests that many of these real-world monsters are indeed spinning at near maximal limits, fueled by billions of years of swallowing surrounding stars and gas. Gargantua is not just a fantasy, it is a highly plausible cosmic reality. Gargantua represents the perfect marriage between the poetic beauty of cinema and the uncompromising rigor of theoretical physics. It stands as a testament to the fact that reality is often far stranger, more terrifying, and more beautiful than anything we can invent in our wild imaginations. Somewhere out there in the sleeping galaxies of our universe, a real Gargantua is silently spinning right now, waiting to be found. If this journey into the physics of Gargantua blew your mind, smash that like button and share this video with your fellow space travelers. In our next episode, we are diving straight into the terrifying reality of time dilation and explaining exactly why an hour on Miller's planet costs 7 years of human life. Leave a comment below with your thoughts. Would you ever dare to orbit a black hole? Until next time, keep your eyes on the stars, and thank you for watching Sleeping Galaxy.